Good morning, calculus.
Hey, good morning.
Got one awesome thing to show you. Let's get to it. While the stragglers get in the house. So we are going to review today, which I think will be very important. First, I need to show you something of utter amazement. So, how many of you are familiar with this? Is just interesting from yesterday, but how many of you are familiar with this little phrase, e to the pi times I power? Have you ever seen that before? Alyssa says no. Type that in your calculator. Find those, like eyes on your calculator. This is one of the great mysteries of mathematics. So let's see, E is above the division sign. Where's I? You never use it, so it's like you got to find it every time. There it is, right above the decimal point. So type E and then raise to the pi times I power. Remember, E is approximately 2.718. And it shows up where you have continuous growth, like a tree or a person, continuous growth or decline. That's where E shows up. And then of course, pi shows up in circles because it's the circumference divided by the diameter of every circle in the world. So circles and continuous growth. And then of course, I is this number we're not really even convinced exists, right? Because I, we are told, is the imaginary number, the square root of 1. And so these are three really ubiquitous and crazy numbers. And yet if you stir them all together into one recipe, what did your calculator say they are?
-1.
-1. Does that bother you?
Yeah, what the heck?
That should bother you. That should bother you a lot. What? That makes no sense whatsoever. Well, I'm going to show you how what we and when I first heard that, I assumed that was kind of like, I mean, I think of all discoveries as kind of being like people mining for gold, and it's, they're just dig, and all of a sudden, oh my gosh, look what I found. And so, I can imagine just some nerds sitting there with a calculator typing in crazy things and suddenly getting -1 or something. But this was discovered long before calculators, and it's actually true because of something we're studying right now. So let me remind you of a couple of things. We're going to need this. What would happen if I took I and squared it? Well, if I square a square root, it gets rid of the square root. So that would make I squared -1. So although I doesn't really exist, it's an imaginary number in a sense. I squared does. That's kind of interesting, isn't it? And then I cubed would then be I squared times I. So that'd be -1 times the square root of -1, or -1 times I. So that'd just be -I. Do you agree with that? You okay with that? I squared times
Yeah.
I, right? So negative times I, -1 times I. And then I to the 4th, of course, would be I squared. So that actually just give us 1. So I to the 4th exists. And then since I to the 4th is 1, then I to the 5th would be I to the 4th times I. And since I to the 4th is just 1, you're sort of back to I again. So I to the 5th is also just equal to I. And so this pattern kind of repeats itself. Does it make sense? This would be I to the 7th. I to the 7th is the same as I to the 3rd. I to the 8th is the same as. So anyway, we're going to need that. Let me show you why. Well, what I'd like you to do this, because this is also a good review for the test. But remembering that e to the x, if I look on my note sheet, maybe you have this one memorized now. Let's see, which one is it? Common Power Series expansions. Look at good old e. What did e to the x? What it expands to? It expands to 1 plus x squared over 2 factorial and so on. If you have this sheet, pull it up because we're going to need it for a couple of things here in a minute, because you're going to have to recognize something. And so, all right, fine. If e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial, very recognizable expansion. So it's equal to that polynomial. Well, then
Can we just plug in pi and I for x?
exactly. So what you do then is go back and take this pi I and just replace it with x. Now, of course, that's just going to look like, yeah, whatever, big ugly mess, but that's what we're doing now. So let's do that. So e to the pi times I, we're just going to replace it with x. So it's 1 plus e, I'm sorry, replacing x. The e is gone. So it's just pi times I, and then pi times I, but squared. And then pi times I, but cubed. And I'm going to go a ways with this because there's something I want you to recognize. Pi times I to the 4th. We're going to go all the way, my friends, out to the 8th power. Got to start writing smaller if I'm going to get that done. So that's pi times I to the 7th over 7 factorial. And then I'm never going to be able to do this on paper again. I can't do this without technology. Scoot that over just a hair more. Now there's room for the 8th. Now again, that might initially look to you like kind of a dead end, like, you know, why are you doing this? Why are you writing so many terms? ... keeps on going forever. But now I want you to start including this business that I just pointed out up here. Although I doesn't exist, I squared does. And I to the 4th does. And notice we got some of those. Okay, I'm just going to give you a second to think about this. So I can't really do anything to the first couple of terms. But then notice that third one in, I got pi squared and I squared. Well, pi squared is pi squared, but I squared is -1. So there's no I in that term, it goes away. So this actually becomes then a negative pi squared over 2 factorial. And leave the factorials alone, don't write them as 24 and 120 and all that. Just leave the factorials alone. Let's see, and so, okay, this pattern works. So then I cubed, we said was just negative I. So I cubed can be replaced with negative I. And then we'd have pi cubed. So pi I cubed is pi cubed and I cubed, but I cubed can be replaced with negative I. So I'm just simplifying the i's. And then I to the 4th, this is very wonderful. I to the 4th is just 1. So all I have on that term is just pi to the 4th over 4 factorial. And then I to the 5th, let's see, I'm looking back up here. I to the 5th was the same as I. So that means the next term would be pi to the 5th, but then just I. I can replace I to the 5th with I. It's the same exact thing. And then pi to the sixth, we said was actually the same as just -1. There's no I at all. So pi I to the sixth is just gone, except it creates a negative sign. And so I have pi to the sixth, but then no I at all. That's kind of fun. And then I to the seventh is the same as -I. So that creates a -I, but then there's a pi to the seventh. So notice the alternating series it's creating. That's kind of interesting. Well, not really alternating. It's like kind of like, actually looks like minus, minus, plus, plus, minus, minus. And then lastly, pi to the eighth we said was the same as 1. So there is no I at all in this term. It's just pi to the eighth. I to the eighth is 1. It's gone. And so it's over 8 factorial. And of course, that just kind of keeps on going from there. Now, again, you still might be thinking, yeah, so. But now I want you to notice all the I terms. All the I terms. Let's see, this one's got an I, that one's got an I, this one's got an I. Notice they're just I now. There's no more I squareds, cubes. There's only I, no exponents on the I. So I'm looking at all those I terms, and I'm just gonna rewrite that. Well, I got kind of two things going on here. I guess kind of the non-I one would be 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial minus pi to the 6th over 6 factorial plus pi to the 8th over 8 factorial. And I think I see a pattern, don't you? Like I could even write the next term, because notice that's plus minus plus minus. So the next term must be pi to the 10th over 10 factorial, and the next term must be plus pi to the 12th over 12 factorial. I think I see a pattern there. And so, you know, dot, 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 there's like half of it. But then, you know, what about those yellow terms? What about those yellow ones? Well, there's every one of them's got an I. So what if I took an I out front and just factored it out? Then I'd have a pi minus pi cubed over 3 factorial plus pi to the 5th over 5 factorial minus pi to the 7th over 7 factorial. Again, I see a pattern, don't you? Like I could actually write the next terms because this pattern's pretty recognizable. It's plus minus plus minus. So this next term must be a plus. And these are all the odd powers. So this must be pi to the 9th over 9 factorial. I guess the next would be minus pi to the 11th over 11 factorial. So I can actually see that happening. And again, that just keeps on going. Are you looking at your note sheet? You should recognize those two sequences. Series, I should say. They're not sequences because we're adding and subtracting them. They're both alternating series.
Sine and cosine.
Sine and cosine. Take a look at that. Raymond's right. You got to be kidding me. So you're saying E, no way, this isn't possible. You're saying then that this green sequence up there is actually, well, let's see, it starts with a 1. Let's all look at this together. Starts with a 1. It looks like that. 1 minus x squared over 2 factorial plus x to the 4th. So the even one is cosine, except for our x is a pi, right? Is that identical? Well, yeah, it's identical. In other words, that green sequence is actually the cosine of pi. Isn't it? Exactly. The red sequence starts out with pi, and well, there's an I out front, but there's a pi and then a pi cubed and a pi to the 5th. Well, look at sine. there's an x and an x to the third and an x to the fifth. Well, that's exactly the same as not the sine of x, but the sine of pi, isn't it? Whoa, where did my note go? There it is. Wow, so this one is actually I times the cosine, not the cosine, but the sine of pi. Seriously? So you're saying, what you're telling me is that e to the pi times I is actually equal to the cosine of pi plus I times the sine of pi? Is that what you're telling me? Yeah, I'm telling you that. Now, again, this just, this is crazy. So not only are e, pi, and I stirred together, which are totally weird, seemingly unconnected, random, I don't know, creatures that roam around in the world of math. And yet you're telling me, hey, they got some friends, cosine and sine, they're in there too. Yep, that is what I'm telling you. Secondly, notice that's not cosine of x. Like think unit circle here. What is the cosine of pi? If I'm at pi, I'm right here, right? That's pi. What's the cosine of pi?
-1.
Cosine of pi is -1. What's the sine of pi?
0.
Sine of pi is 0, which is kind of a good thing because I remember it's sort of like a weird number. Sine of pi is actually 0. And so, well, there's the reason why e to the pi I is actually -1. This was discovered. That's the thing that blew my mind. This was not found like by someone randomly tripping over it in the forest. This was discovered to be true. This was made. It was not found. That is unbelievably cool. So there's two things like about this. One of them is you got to have an understanding of infinite series to even kind of entertain this idea. But two, look at the beauty of math here. I mean, this should leave a sense of wonder in you. As I've pointed out before, this makes people philosophical. Like, what's going on in the universe? That all of this stuff is connected somehow. What's going on? It just sort of feels like we're touching something bigger here. We're touching something that's like, it just doesn't make sense that somebody would decide, hey, I got sheep and you got sheep. Looks like I got more. What is that? How do you think of numbers as being invented somehow? It's like, how do you compare that I have more sheep than you have sheep? You sort of think of a caveman or something. And you think of numbers as kind of starting like that. We got to have some way of kind of knowing how many sheep I have. And so somebody invents numeration systems. It's really interesting to study numeration systems because not everybody's the same in that regard. But anyway, I won't go down that trail. But wow, what a wondrous thing. Unbelievably cool. So anyway, that's a little bit of good practice just to recognize probably the three classics of all the things that you want to be able to, kind of take away from this. It's probably those three right there that are kind of the biggies. Those expansions are what allow us to know what the derivatives and integrals of sine and cosine are and of e to the x. And that's kind of our reason and our proof as to why those exist. That's the reason we have a calculator. And so that's kind of cool. All right. I want to ramble about that longer, but I think we better get after some review. Let me see, did I put that in here? Yes, I did. So you will have this sheet for your test to the extent that you need it. And as I mentioned yesterday, I want you to be able to make things like this for yourself, but I also want you to be able to use these, which is what we did yesterday. We didn't make these again, we used them. So as an example of using them, let's just do that right now. Like if I said, if I told you f of x is equal to x times e to the x, does it make sense you could do Taylor series? Like you could take the derivative of that. You could take the function itself, its derivative, its second derivative, its third derivative, But you can appreciate the derivative of that'll be a little painful because that's the product rule, right? So let's just play with this example for just a minute. So let's do the Taylor series. Now, again, we got to center this at something. In other words, we got to decide, I want to find a power series for this, but I want it to look like this. But the question is where? It's not going to look exactly like it unless we have infinitely many terms. And so where do I want it to look like? Well, I want this to be easy for me because I'm lazy. And so I'm thinking, let's let x be 0 because e to the 0 is 1. That seems like a smart thing to do. And so let's center this at a equals 0 or x equals 0. So according to, and this is the big takeaway for everything that you're going to see on this test. So I say, okay, great. If that's true, then what's f of 0? Well, f of 0, I get 0 times e to the 0, I get 0 times 1, so it actually still stays 0. So that term, if you will, just kind of doesn't exist. And then I say, okay, cool. Now we're going to go get the derivative. Unfortunately, product rule. Derivative of x, which is 1 times e to the x left alone plus x left alone times the derivative of e to the x, which is also e to the x. And so, great. And so what is f prime when evaluated at 0? Well, this term is going to go to 0 again because of the 0 in front of it, but this term isn't. That's 1 times e to the 0. That's actually 1. So we got an answer for that. And okay, proceed. This is what you do to find the power series yourself by hand. Second derivative. Well, the derivative, I've got two different terms here, so I got to find them both. So derivative of, fortunately, e to the x is e to the x. Cool. And then x e to the x is, well, the same thing we just saw a second ago, which is e to the x plus x e to the x. So there's the product rule again. Stop me, interrupt. So if I said, okay, well, what's the second derivative then evaluated at 0? Again, the reason we're doing this is we're trying to get the slope to match. We're trying to get the point to match, then the slope to match, and then even the change of the slope to match. And so this would produce a 1, e to the 0 is 1. This would produce a 1, this would produce a 0. So now we're up to 2. Let's do one more and then we'll quit. Third derivative. Look at all those plus signs. The derivative of e to the x is e to the x. The derivative of e to the x is e to the x. The derivative of x e to the x is a product rule question, which we already saw was e to the x plus x e to the x. So you end up with, if you put 0 into that, you end up with 1 plus 1 plus 1 plus 0. You end up with 3. I think I see a pattern. Do you see how this is going to happen every time? I can tell what f prime of 4 is going to be, or f, the fourth derivative of f, it's going to end up 4. But we can stop right there. And so what does this expand to according to Taylor? And remember, technically, because I said this is centered at 0, there's another name for that, Maclaurin series, but it's better just to call them all Taylor series. And this one happens to be around 0, fine. So Taylor series said if you take f of 0, it's time to change colors. Our new function that is also the same as the old function. That's why I'm giving it the same name. Our power series expansion is the value, and again, stare at this note sheet because I want this to speak to you. That's our first thing. F of whatever, 0 in our case, A is 0. So that's our first one. Oh, it's 0. Okay, fine. And then our next one is, what does it say? It says the first derivative divided by 1 factorial multiplied by x minus a to the first power. So for us, that's 1 divided by 1 factorial times x minus, well, 0. So it's just x. And then our next one is 2 divided by 2 factorial times x minus 0 squared, and then 3 divided by 3 factorial x cubed. And so again, this is kind of cool because I can actually see a pattern. Like I can tell what's happening here beyond what I what I calculated. I made it to here and I would have to quit, except for look at that pattern. That's beautiful. I can actually tell what's next. It's 4/4 factorial times x to the 4th, and so forth. Okay, great. But just to make this look a little cleaner, do you agree that 3 factorial is really 3 times 2 factorial and 4 factorial is really 4 times 3 factorial? Why am I writing it like that?
Simplification.
Yeah, because it's going to simplify. So I end up with x plus x squared plus this 3 cancels with this 3. So I just end up with x cubed over 2 factorial. And this 4 cancels with this 4. So I end up with x to the 4th over 3 factorial. So I think, again, I think I see a pattern. The next term must be x to the 5th over 4 factorial. The next term must be x to the 6th over 5 factorial. And so I think I see where this is going. So I think I found the answer. I did this, as I will say on the test, by hand. I didn't cheat. But how could I have cheated? This is what we did yesterday. How could I have cheated to get this answer if the original problem was this? Well,
Could you have just taken the e to the x series and multiplied everything by an x?
exactly. Like we've already expanded e to the x before. We already know what e to the x is. So couldn't we just take that and multiply everything times x? Like, isn't that the easy way? So kind of first doing this the hard way, we got this answer, but redoing this the easy way, using the table, then couldn't I just say f of x equals x e to the x is the same thing as x times, well, what did e to the x expand to? It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on and so forth. So if I multiply x times distribute x into every one of those, doesn't that turn into x plus x squared plus x cubed over still 2 factorial, 2 plus x to the 3rd now goes to x to the 4th, but it's over 3 factorial. It's like, oh, look at that, I'm already done. Same exact answer. Cool. Same. So that's kind of neat.
Hey Doug, I had a quick question.
Connor?
In one of the problems it says use the Taylor series to estimate a different location. So like the common one was like natural log of x, and then estimate natural log of 2. Do we have to change our center in order? Because at this point, like if we were doing that, we would just plug in 2 for x, right?
Yeah, so does it make sense? Now we have a model. We have a model for x e to the x. So in terms of using this for something, and this is kind of what, if you will, the ancients did with it. So if we wanted to use this, get rid of some of this gobbledygook, clean this mess up a little bit. So let's say we actually found this model for it. And again, I'm going to replace that f of x with the fact that this is x e to the x. And so the ancients had no way of dealing with this. Does that make sense? The e to the x was kind of a problem for them because they, it's an exponent and so forth. And then e is not even perfect. And so they didn't have any problem with 0. Does that make sense? E to the 0, they knew that's 1, no problem. I can raise e to the 0 power. But what if they wanted to estimate, if that's equal to f of x, what if they wanted to estimate, well, something close to 0, like, I don't know, 1. Does it make sense they would know that one too? because e to the 1 is e. Like I don't really need the green expansion for that. I can say, well, that's 1 times e to the 1. I mean, that's just e, and I know e is about 2.718, so I don't need that expansion. But what if somebody said, I'd like to know it for something like 0.2? Now 0.2 is pretty close to 0. Does that make sense? That's what Connor's getting at. We made this look the same. We made these look the same, but right around 0. So what we're thinking here is if somebody wanted to put in like 12, this might not work. Right? Now, remember, this is what the radius of convergence thing was. And remember how that worked. Like for some things like E, did E have limitations? Was there anything I couldn't let E be? Look at that. No, I can use anything I want. So it's okay to do 12, but why might 12 not be very good? Why might that not be a very good estimate?
You need a huge amount of terms, right?
Might need a lot of terms because 12 is so far away from 0. But 2.2, that's really close to 0. 0.2 is going to be excellent. Do you understand that? So if you will, the ancient person could say, hey, I think I'll, use this 6th degree polynomial up here as an estimate. I'll put 0.2 into that. Now, again, in our world, we'd be using calculators for both of them. And so we'd sort of think, the green one's a waste of time. It's going to take me longer to find it there than just to put the thing into the, original. So that's kind of interesting. But just for the fun of it really quickly, and that's the kind of thing you would do. And so you're putting something in close to it. So let's actually figure out what f of 2 is. And notice I'm just using that equation because I have a calculator. If I say 0.2 times e raised to the 0.2, I'm getting approximately 0.24428055516. This is kind of like the correct answer. What's our approximation of that? Again, this takes a little bit of time to type in, but that's kind of cool. So 0.2 plus 0.2 squared plus 0.2 cubed, but divided by, this isn't going to take forever, divided by 2 plus 0.2 raised to the 4th, but divided by 3 factorial, which is 6, plus 0.2 raised to the 5th, divided by 4 factorial, which is 24. We're almost there. Plus 0.2 raised to the 6th, divided by 5 factorial, which is 120. If I didn't type that in wrong, and I'll be able to tell because I should get about the same answer. I got 0.244280533. Look at that. That is incredibly accurate. Do you see how long it takes before they don't even match? Like 2805. It's this term right here. Oops, that's not what I wanted to do. It's this term right here. That's the first one they don't line up with. Wow, that's an incredible estimate. And we did it just using normal numbers, if you will, nothing weird. So yeah, I would ask you on a test to approximate something using your expansion. But again, we do have to choose how far to go. And notice this choice was too far. We didn't need that many terms because it's just ridiculously accurate. Make sure you use Desmos on your test. Graph both of them to make sure they look right. I won't take the time to do that right now, but graph the original, graph yours, and make sure they look the same right around the point that they're supposed to be the same. They're supposed to be the same right around 0. And so apparently they are, because look how good those two answers are. So the estimation is a little bit obsolete for us, but that's just kind of cool. So let's take a look at these questions that I gave you for today to consider. And I said what I just told you right here. Verify your work on Desmos. You will have this lecture on the test as well. I think this is kind of cool. If you look at this problem right here, notice I said from scratch. And then you wouldn't have to do this one from scratch. Do you agree with this? Why wouldn't you have to do this one from scratch if I didn't ask for it?
Because you can use the natural log series that we already have.
Yeah, we already have natural log of x plus 1. That's on our sheet. And so natural log of x plus 1 is going to create a bunch of, well, x squareds and x cubes and x to the fourth. So notice all I would have to do is just add another x squared to it and add a 3 to it, and then it would be the same. And so that's kind of cool. But you should also be able to get this, well, by taking derivatives and so forth. So that's the flavor of what I'm going to ask on the test. Like, can you do it the easy way? And can you do it the hard way? Get the same thing. That's just kind of good. That'll help you kind of feel like, yeah, I'm getting this right. Or, you know, writing me a note about something's not right. And graph it to kind of make sure it works. What's with this C thing down here? Find the derivative and compare it to the original derivative and show they're equal. That's kind of cool. Remember, that's what this is all about. And so let's do that part of this right now. Let's just kind of play with that a little bit. So I'm not going to do this from scratch. I'm going to cheat. I'm going to use the cheat method. So I'm going to do B here, which says show your answer from A. It could be found more easily by just adding x squared plus 3 to the expansion for natural log of x plus 1 given on the note page. So I know the expansion for natural log of x plus 1. Again, notice how few of these there are. Because I mean, I could have made that the natural log of x squared, for instance, and then you don't have a sheet to cheat from, right? And I will do that some. But we have some of them. So awesome. Well, here's one of the classics right here. Notice it's pretty memorizable if you had to memorize it, because it starts with x and then it's x squared x cubed, but then it's plus minus plus minus. And then notice it's not factorial, it's just divided by 2, divided by 3, divided by 4. So that's what that is. And so, okay, great, I can write that out. So the natural log of x plus 1, we are told, is x minus x squared over 2 plus x cubed over 3, apparently minus x fourth over 4 plus x to the fifth over 5, and so on and so forth. Double checking to make sure I didn't screw up the signs on that. I did not. And so then all we're going to do is add x squared plus 3 to that. Okay, that's easy. So then that'd be 3. So notice it didn't have a constant in front of it. Now it does. And then the only thing x squared interacts with is the x squared term. And so if I have one of them and I subtract half of them, don't I now have plus one of them? And then everything else stays unchanged. Do you agree with that? Now notice it's interesting because it screwed up the pattern that was so recognizable. But if you will, from here on, the pattern is intact. So the 3 and the x squared screwed up the constant and the x squared term. Oops, I forgot the x term, didn't I? One of you would have told me that in a second if I didn't see that myself.
I was just about to say that. I was like, I got random X in the middle.
Yeah, there's an x there, and I forgot that. So basically our 3 and our x squared screwed up 2 of our terms. It screwed up our constant in front, which was 0 in this case. But everything else is left unchanged. And so there's our answer. We're done. There's an expansion for the natural log of x squared, x plus 1 plus x squared plus 3. And again, it's fun to go into Desmos and graph both of those and make sure that they work. So much fun that I can't help but do it. So we're saying that y is equal to, and again, that's just kind of fun to think about. You know, we're taking a parabola and adding it to natural log. So that's kind of crazy. Why would, you know, who knows what that graph is? And we've never graphed that before. So there's natural logs graph. And so you may remember, yeah, that's what natural logs look like. Plus 1 made it slide 1 to the left, but then I'm going to add a parabola to it. That's crazy. So what's going to happen if I add a parabola to that thing? Oh, that's kind of cool. That's a fun looking graph. I like that. Stretch it out so it looks a little more visible, looks like the side of a wine glass or something like that. And now we're saying that's actually the same, it turns out, as the graph we just found, which was 3, not plus, but equals 3 plus the x was unchanged. And then it would have been minus x squared over 2, a half x squared, but then it became plus x squared over 2. So the question is, do you see it? Are you watching it grow to become the same exact graph? Notice it's centered at 0. So it's a match at 0. It's not a match away from that yet, but it's as good as it could get right now. Look at that. It's excellent. And then I just keep adding terms. What was the next one, minus or plus? I forgot it. Minus, it was plus. Yeah, it was plus. So if I add a cubed term to this, and then I divide by 3, it's just getting better and better and better. So, you know, you don't need me to grade this. Does that make sense? Like, look, it worked. Cool. I know I'm right. Brag a little bit on the test. Talk some smack. Tell me you know it's right. Don't bother grading this. Use mine as the key, stuff like that. Notice it's kind of cool. Again, remember what 4th degree equations do. This is a negative. What's the most dominant term there? It's the 4th degree term. And notice its coefficient is negative. Well, that's going to be a downward facing kind of a W shape. Well, it turns into an M. So, you know, of course it looks like that. If I add the 5th degree term, then it's going to come back and make kind of an S shape again. And so, yeah, look at that. It's following it beautifully. And so that's what you should be doing on the test, is kind of checking that, making sure everything's working good. So that's kind of cool. That's actually a polynomial. And so again, you might say, hey, I got a new representation of this thing. Awesome. And so as we've said, it's basic math now. You don't have to have a logarithm button, which nobody had historically. And it's just a polynomial. Therefore, if I need an integral or a derivative, I could take the derivative or integral of this new equation, which is an exact match. Well, it's an exact match as long as we say ... goes on forever. So that's the flavor of the kind of questions I want you to do. Now, find p prime of x and compare it to f prime of x. Can you take those two derivatives? I mean, they're supposed to be the same thing, right? And if you wanted to prove that you got it right, the easiest way is to do what we just did and graph it. But the idea is, could you take the derivative? So here's my again, this is a little confusing. It's confusing to me too. Is that P5 or is that P6? In other words, is the 5 referencing the fact that it's 5th degree, or is it the summation from n equals 0 to 5, which actually would have 6 terms, right? Since you started at 0. I'm not going to ding you for this on a test, because that's just, you know, I'm not exactly sure myself when I stare at this, because, you know, the original natural log of x equation, let's see, 1st, 2nd, 3rd, 4th, 5th, that's got 5 terms and it's 5th degree. So I probably can't get this one wrong. Does that make sense? I think I got this one.
My instinct would be to say it's based on the power of the polynomial, because like the C5, C6, whatever, all that cares about is the power that is attached to.
Yeah, it's kind of a question of like, does this mean, you know, p to the n, and so it's the n equals 0 to 5, and so yeah, so I actually don't care. Like, I'm just saying stop at some point. So the question is, would you agree the derivative of P5, well, notice how easy it is. The derivative of 3 is 0. The derivative of x is 1. The derivative of x squared, the 2 comes down front, cancels with the 2 down below. And so it just leaves x. And then x cubed, the 3 comes down front, the 3 cancels with what's below and just leaves x squared. And so isn't this nice? And then minus x to the third and then plus x to the fourth. And that's kind of cool because I can see the pattern from then on. So that's the derivative. The question is, since f of x was equal to natural log of x plus 1 plus, we said x squared plus 3, the question is, will I get the same exact derivative? I mean, I should, but notice it doesn't feel like it, right? Like I'm thinking, really? It's hard to believe. It's going to look like that. Well, the derivative of natural log of junk is 1 over the junk. And so that's not good because that doesn't look anything like it. And then plus the derivative of x squared is 2x and the derivative of 3 is gone. And so we failed, right? That doesn't look right at all, does it? Any ideas? We didn't fail. Like we looked at the graph. We have this right. How come those don't look the same? How come this doesn't look anything like this?
Now we have to expand it, right? So,
Yeah. Isn't there other ways to write things? Isn't 1 over 1 plus x expandable? So it doesn't look the same. But one of the surprising things of this whole section is the fact that you now have new ways to write equations. You don't ever, and if you're going to compare them, they both have to be polynomials. And so unfortunately, 1 over 1 plus x is going to have to be rewritten. And notice it's easy pattern. It's plus minus plus minus plus minus, and then it's just 1 and then x and the next squared, not divided by 2 or divided by 2 factorial. So first we thought we were thwarted, but we are not thwarted. Because this, I need a new color, that we just saw was actually 1 minus x plus x squared minus x cubed plus x to the fourth. And so I can actually add 2x to that now. What do you notice if you do that? If I add 2x to this, the only term it affects is that term right there, which makes it actually turn into a plus x. 1 plus x squared, 1 plus x squared minus x cubed plus x to the fourth. Oh my gosh, they are the same. That's really cool. Do you see how playful the questions I'm asking are? And, you know, I'm going to ask a lot of questions about, you know, one problem instead of just 10 different questions. Because it's just weird. In a sense, we're like juggling now, like we're showing a sense of mathematical coordination by just playing around. We're playing with this problem we were given. We can do it the hard way. We can do it the easy way. We can take derivatives of both of them, show they're the same. But even that involved us having to replace this statement with something else it's equal to. I mean, that's just kind of cool. So the graph was the easiest way to check, but we've proved this every way possible. So let's look at these last 4 examples here. So do you see how this next question is exactly the same in the sense that I said, consider the function x times the cosine of x? Well, that's a product rule problem if you're going to do it, as I said here, from scratch. And I did warn you about that, as I would on the test, because it's been a couple terms. I could see somebody screwing up the derivative on that. You were good at it back, 6 months ago, but so the derivative of that is a little bit ugly by hand, but notice it's super easy you already know if you're allowed to use the note page, you already know the expansion for the cosine of x, and then just like we did with e, just multiply by x. And you should get the same exact answer again. So that's kind of cool. And then take those 2 derivatives and see if those are the same too. Very playful. This is a cool question. Take the derivative of the power series expansion of sine and show that it's exactly the same as cosine. Since the derivative of sine is supposed to be cosine, then could you bust out the sine of x, this statement right here, and then take its derivative and show that, yeah, sure enough, that is exactly what's listed right here now. And so, yeah, the derivative of sine really is cosine.
Can we run over the integral problem? I think this
Yeah.
problem.
So number 4, taking the integral, and this is, by the way, did I save this? engineering. Was this yesterday? Yesterday, we started off with a statement really similar to this question that's on the review. And I was bothered by the fact that it didn't work right. That's because I put this correctly in the notes, but I had the 2 outside of the square root and it's supposed to be inside the square root. So I actually fixed that in the notes. But the problem here is you're taking the integral of something and it's just too ugly to take the integral of e to the x cubed. That does not work by normal techniques. And so that's terrible. Yet, if you rewrite it as just a polynomial, integrals of polynomials are easy. Let me give everybody a chance to kind of think about that. Notice I said, and if I give a question like this on the test, I would not want you to make for yourself the Taylor series expansion for e to the x cubed. I would want you to notice, hey, we have an expansion already for e to the x. And so all I have to do is replace x with x cubed. And then I'm done. I have it. I don't need to build it from scratch. I'll kind of be really clear on the test. You don't have to do this from scratch. You do have to do this from scratch.
So
So
this is kind of like the modern way that you would use the Taylor series, huh?
yeah, that's right. Once you've built this table for yourself, and that's to me, the cool takeaway is to go build all 8 of those yourself. Yeah, that's rad. I know where those come from now. I got them. And then you never build them again. I'll just use those. Anytime they come up, I'll use them because those are, those are the big ones, logarithms and trig. The only reason those top 2 are on there is because they're so beautiful and simple. But
Well, and because you said that there are certain integrals that it's impossible to take. So is this something that you would do in real life as an engineer? Like you're like, okay, I don't know if that's a really ugly integral. I'm going to take the Taylor series of it.
no, because you could type, you said doing this as an engineer. No, because you could just type that into Desmos and get the answer.
Oh, yeah, I guess that's true.
So everybody that was an engineer before, well, Desmos is only, well, I guess your graphic calculator would do this, but our technology in the last 20 years has allowed us to cheat to get this answer so that we don't have to do this. But everybody historically before this that wanted to know the area under some curve for some practical reason, or maybe just because they were curious, wouldn't have had a choice. So it is kind of interesting. One respect, this is an obsolete. And by the way, there's lots, when I went through college, I didn't take this class. I have a math degree. I never took this class because it wasn't required. And that's because it is a bit of an obscure kind of a topic. It's neat, but you don't need it for things that are kind of later on in math, and you don't need it in the real world super often either. If you're taking differential equations with me this summer, that I that was just in cosine a little while ago, we're going to use that for something really cool. Hopefully you are taking that with me this summer. You don't want to miss that. If you have any free time or free mind at all, it's like that's a topic you don't want to not know. It is really cool.
Take which one? You said Calc 4.
256. It's not Calc 4. It's differential equations, which is required for engineering types. But I'm actually saying that out of personal interest, even if you don't need it. But it transfers to all other schools as a 300 level math class. So you might look into your degree program because it'll be easier here and cheaper, if you will. And I teach it from a practical perspective just because I think it's so cool, not from a theoretical perspective. So it'll make it a little easier for you to grab onto. That's why I'm saying it's going to be easier.
Real quick, so since that's during a summer term, is the workload like really heavy, or
No.
do you have to cut stuff out?
We do it in 8 weeks, but we meet for longer each day, which actually works really good because we meet for approximately an hour and 50 minutes. You notice how every day here we're always kind of like 20 minutes away from being done. I mean, we can quit, but it sort of feels like this class, it feels like the right amount of time for a lecture. So no, we just do what we can get done in 8 weeks. So
Calc 4 is not a prerequisite for it, right?
no. You all have the prerequisite. This class is
Cool.
technically a prerequisite to it, but it's because of something I'm going to show you that involves what I'm teaching you right now. But I'll be able to, I'm going to basically bust out this sheet right here and show that to the people that didn't take Calc 3, and armed with armed with just this part of it right here, they want to understand why, why it is and where it came from and all this business about convergence and how that actually results in some. They won't have the depth of understanding you have of it, but they'll be able to use it. If I just say, hey, this is true, and they go, okay, they'll be just fine. So thought I wrote e to the x down someplace. So since we know what e to the x is, then all I'm really doing then is taking the integral of, well, e to the x was 1, and then plus x, and then plus x squared over, was it factorial? Yeah, it was factorial, plus x cubed over 3 factorial. I think that was e. I'm just replacing all of those x's with x cubes. That's it. So every place there's an x, x cubed. So my series then just looks like this: 1 plus x cubed plus x cubed squared, that'd be x to the 6th. And then x cubed cubed, that'd be x to the 9th. And again, notice that's a recognizable pattern. Like, oh, look at the powers. They go from 3 to 6 to 9. I'm adding 3 each time. So I actually know it's a recognizable enough pattern that I could write the sigma notation for it really easy. And I can recognize what the next term would be because of the factorials. And so, oh, okay, well, that'll be a super easy integral to take, you say. I can take the integral of that now because it's a polynomial. So you would say the integral of 1 is x, the integral of x cubed is x to the 4th over 4, or 1/4 x to the 4th. The integral of x to the 6th is x to the 7th divided by 7. So 2 and 7 would make 14. X to the 9th would be x to the 10th, divide by 10. 10 and 6 would be 60. So on and so forth. So now I just have to plug in 1 and -1 to that. And do you see how plugging 1 in, 1 to the 7th, 1 to the 10th, the coefficient of 1 over 60, you can see the terms becoming less and less important. So again, I'm just getting an approximation. You can't find the integral of e to the x cubed. At least not easily. So we're saying carry it out as many terms as you want if you evaluate that at 1 and -1. That's kind of a cool application, I think. And of course, again, you have the luxury of going into Desmos or your graphing calculator and cheating to get the answer, and then seeing if you got the same thing. And so you should know you got these right or wrong.
Hey Doug, a lot of the 11.4 homework is kind of building the Maclaurin like equations. Is that something we're going to have to do on the test as well?
I'm going to ask you to build a little bit. And that's kind of what we did with the first part of this. Like, we built the Maclaurin series. The very first thing we did here was build the Maclaurin series for x e to the x. So it's better just to call them all Taylor series. It's just the Maclaurin is when a happens to be 0. It just makes your equation look a little nicer. Instead of x minus 7 and x minus 7 and x minus 7, it just says x. And so in a sense, they're all Taylor series.
Well, I was kind of talking about when they get the like sigma in there and then it's -1 to the k power, you know.
No,
that.
there's not going to be, I'm not going to make you write sigma notations for things.
Okay, perfect.
which is, again, I could easily make this test, make you all fail this by saying you have to write sigma and you have to give me the radius of convergence, because that can be really tricky. But I just think that I'd rather you spend your time with the beauty of this. And then if you love math and, go on and want to look into that a little, or even stay after class and look into it a little more deeply as to why that is, we certainly can. I mentioned going out the door yesterday that, and I'm sure if all of you are still here, but just in that same vein, either we or someone smarter than us took the time to write, I guess this one is cosine, write cosine like this. And so notice the radius of convergence is infinity. In other words, you can plug in anything you want. Well, you can use, as I mentioned, going out the door, the ratio test to produce that. If we took that statement up there, and again, not this part of it, but just the x to the 2k over 2k. And then we added 1 to that. In other words, 2k plus 1 and in both cases, and we put 2k plus 1 on the top and then the k on the bottom. And we divided those to see what limit it approached. Basically, it's going to approach a limit of 1 always, no matter what you do. I think I will say that really quick. You can ignore me and work on other review things, but let's take a look at this. What would that be? So ratio test, I'm just going to squeeze it in here so you can see it. Ratio test would be, we're going to replace k with k plus 1. So notice that's 2k plus 2. So I end up with x to the 2k plus 2. Again, I don't like k so much. We're used to n, but and then on the bottom it'd be 2 times k plus 1. So it'd also be 2k plus 2 factorial. And that's divided by an, just the original. So it's just x to the 2k over 2k collectively factorial. So what does that become? Well, I would have x to the 2k plus 2. Do you agree that that's x to the 2k times x to the 2? And on the bottom, 2k plus 2 factorial, that'd be 2k plus 2 times 2k plus 1. Isn't that how you find factorials? You just subtract 1 from it each time. And then the next one would be 2k. And so I could just stop right there and say that from then on, it's just the same as 2k factorial. And then I'm dividing by this, which is the same as multiplying by the reciprocal. Maybe now you see why I expanded those the way that I did. So look at all the stuff that cancels out. So this cancels with this. 2k factorial cancels with 2k factorial. And so now the question becomes, what happens to x squared over 2k plus 2 times 2k plus 1? What happens to that according to the ratio test as k goes to infinity? For some x is 10. Remember, this is like, x is 10 or x is 20 or x is 50. X is some number. Well, if k is infinity, look what you have on the bottom. You have 4 infinity squared. This is going to go to 0 no matter what you pick for x. That's why this says up here that x can be anything. There's no limitation, because the ratio test said as long as that limit approaches something less than 1, you got to converge. It's going to converge. And we're basically saying, well, look at that. You could pick x to be any number you want here. A number, not infinity. Infinity is not a number. Pick 10,000 if you want to. 10,000 over infinity squared is 0. It's on its way to 0. That's why this radius of convergence is infinity. That's why I can pick any number I want. So if we had more time in this class, maybe I would include that. Maybe this section would go another 3 or 4 days and we'd spend time with this a little bit more, and we could, and maybe arguably even should. But I've given you a dose. I've given you a sense of that. I just don't think it's worth testing on, and I don't think we've talked about it enough to be tested on it. But that's where that stuff comes from. And so the difficulty is you actually have to be able to write sigma notation to even do what we just did. Sometimes that's very hard. Anyway, that's a side note.
Could you give us an example of something we wouldn't use from the note sheet?
You wouldn't use?
Like you said how
Oh, right.
on
You're
some
not-
of them.
you're just on your own. Yeah.
Yeah.
Yeah. So if I make up any function I want that just isn't on that sheet. So I could just say, how about so I can't pick sine or cosine. I could pick tangent, but I'm a little worried, like, why isn't tangent on that list? It could be that its derivatives are really weird and so forth. So I'm a little reluctant to try something with trig. I can't pick anything that's like a polynomial, but what about something like the square root of x squared plus 4? This is probably worth our time. Let's finish with this. Now I would like, and let's pick it at a or x is equal to something that makes this nice. I don't want to pick x as 1 because then that's the square root of 5, right? And I don't have a nice clean answer. I'd like some clean answer to this. So let's see, what could that be? Well, I could fix it. Like I could just say I want x to be 3. 3 squared is 9. 9 plus 4, that doesn't work good, right? But 9 plus 7 works good. There. So that's not on your sheet, the square root. So the question is, could you use the Taylor series formula to create a polynomial for that? This is a good test question. Could also word that centered. Centered at 3, that'd be the same way of saying it. So I'm going to launch into it a little bit with you now, since I give you a bit of a head start. Now I made this up from scratch, so maybe this is painful, I don't know. But notice f of 3 squared is 9, plus 7 is 16. Oh, that came out nice. The square root of 16 is 4. So there's my first coefficient. But then I need the derivative of this thing. And since it's really x squared plus 7 to the 1/2 power, and hopefully algebraically, you know, you can't take the square root of x squared and the square root of 7 separately. If you could, that'd be x plus the square root of 7, and you'd be done, because isn't that a polynomial right now? But unfortunately, that's not true. So the derivative then would be, let's see what happens. Well, chain rule, I take the 1/2 out front, and the junk inside stays unchanged while I attack the outer function. But then I have to go on and say times the derivative of what's inside. That's chain rule. So let's see, what is a better way to write that? Well, the 2's cancel, and that would put the x squared plus 7 down on the bottom. So that'll be an easier way to plug 3 in. So I end up with 3 over the top of 4. So f prime of 3 is actually 3/4. There's our second coefficient. Woo, this is not a good example because the derivatives are about to get ugly. Notice that created either a product rule or a quotient rule problem. So this is not a good test question for me. You got to be pretty good at Calc 1 to survive this next derivative because it's ugly.
So
How
the
many-
first part of Taylor series, you just plug in 3 to the original problem though, right?
Yep.
Okay, just making sure.
How many terms do you want us to go to?
In this case, we better stop after one more, right? Because the derivatives are really horrible in this case. It doesn't mean you shouldn't be able to do them, but you can congratulate yourself from being still pretty good at Calc 1 if you can still do this. I think I'm going to use the power rule. So I'm going to rewrite f prime of x. Since the 2's cancel, it's really x times x squared plus 7 to the negative 1/2 power. So what is f double prime then? I'm going to do the product rule. So the product rule says derivative of x times the other junk left alone plus the x left alone times the derivative of that other junk. Well, the other junk would be the negative 1/2 comes down front. The junk inside again stays unchanged. I take 1 away from that. So now it's down to -3/2. And then I got to multiply by the derivative of what's inside again. So, woo, the derivative is ugly and getting uglier. But so that I can plug 3 into this, I'm just going to write it so it looks a little nicer. That's really what the first term looks like. The second one would look like this. The 2's cancel. I have a negative, not a positive, I see. So I'm going to change that to a minus sign. And there's an X on top since the 2's canceled, and the square root's on the bottom, except it's not just the square root, it's actually the square root of x squared plus 7, but that's actually cubed. So maybe now in my head, I can actually figure out what is at 3, where I'm trying to get this all, I'm trying to get these two graphs to look identical around x is 3. Let's see, what would I have? 1/4, since we already know what the square root of x squared plus 7 is.
Doug, even though the 2 canceled, don't you still have that x on the right? So shouldn't it be x squared on top?
Oh yeah, I forgot one of the x's, didn't I? There's 2 x's. Thank you. Good catch. Again, how am I going to catch that if that's me on a test? Well, when I graph them, they're not going to look right. And I'll know if something's wrong. Hopefully I'll catch it. So minus 3 squared is 9. Okay, great. 3 squared plus 7 is 16. And you can actually square root that first or cube it. If I square root 16 first and get 4 and then 4 cubed, I get 64. So that would be times 16 times 16, that'd be 7/64. So there's my third coefficient. Woo! And I don't want to do this again, right? Because I got to take the derivative again. Woo! Now it's really going to get ugly. But I could do it. It's not impossible. Frankly, you should be able to do it. So what we're creating then here, if we quit here, is a P3. We have 3 terms. A cubed. It's a cubed equation. So I know, according to the Taylor series formula, that f of 3 is my first number, and then my coefficient 3/4. But then that's now multiplied by not x to the 0, but x to the 1. And then divided by 1 factorial. Except for it's not x this time. What is it?
X minus 3.
Because it's centered at 3, it's x minus 3. And it's not what I wrote, it's with parentheses there. And then it's plus 7/64 times x minus 3 squared. But what did I forget here? What am I forgetting?
The 2 factorial on the bottom.
Yeah, remember it's 0 factorial, 1 factorial, 2 factorial. So initially 0 factorial and 1 factorial are just 1. And so they kind of don't have an effect. You're probably better off to write 1 factorial and then simplify it, even though 1 factorial is just 1, because it would be easy to forget that. And remember, this last term might be small enough that it won't look terrible if you do. So that's not 64, it's actually 128. So now I think I have a P, well, what is this again? P2 or P3? Again, I find that kind of confusing. Technically, I think this is P2 because you're letting in B2. So I guess I'll just write it that way. P2, N is 2. Technically, that's the right answer to this. So I think I have a good model. Now I want to graph it and so forth and make sure they look the same. And then again, maybe I could use it for something. So some ancient person was saying since f of x, I'm not going to probably ask you this on a test, but since, here's your statement right here, and they all knew what f of 3 was because that's a perfect answer. Awesome, it's 4. But, what about f of 4? Well, they can't answer that. Or even f of 5, 5 squared is 25 plus 5 is 32. And so they're sitting there with the square root of 2 and they're saying, I don't know how to get that. I don't have a calculator. They could estimate it. Well, notice we can estimate it. You could actually throw 5 into this statement right here and have a really, really good estimate. That's pretty cool. without a calculator. And that's all just basic math, right? Isn't that kind of cool? So 4 plus 3/4 times 5 minus 3 is 2. 2 times 3/4 is 6/4, which is 3/2. For the next one, I'd have 2 squared, which is 4. 4 times 7 is 28. So I'd have 28 over 128. So here's my estimate. 4 plus 3/2 plus 28 divided by 128. I just got approximately 5.719. There's my estimate. Notice that's pretty reasonable. 5 squared is 25, 6 squared is 36. What's the square root of 32 actually? According to your calculator, 5.657. Hey, that's pretty good. We only had 3 terms. We kind of wimped out early, and yet we still got a pretty decent estimate. You can kind of tell if we had one more term, it'd probably be awesome. So I will open up the test tomorrow at 8, kind of just normal class time, because I want you to take it normal class time. A few of you have emailed or texted me with issues that came up and so forth, and I'm happy to accommodate those. So that'll open up as normal. You basically have 2 hours, but I'm giving you sort of an extra half hour to get it back to me. I very much want it inside of my open math, so save enough time to get that done. I'm giving you kind of I'm giving you 2 hours and 15 minutes, because probably 15 is enough to get it back into my open math, because it makes it faster for me to grade it, because I'm going to try to grade it. I mean, in a sense, I don't see it till Monday. So you would, if it was a normal class, you wouldn't know what you got till Monday, but I'm going to try to grade it, like immediately, like Thursday, so you can know, because you're probably curious. And if you help me by getting it back in my open math, that'll help me get it done for you a little bit faster. So I think we played pretty good today with kind of the flavor of what you're going to see on the test. If any of that is bugging you, for sure, stay after right now and let's discuss it a little more. Otherwise, it's 9:23, so vamoose yourself.
Could you explain the your thought process behind 2C?
Yeah, so x times the cosine of x. So since this is the cosine of x, all I have to do is multiply x by it and I'm done. If I was allowed to cheat, I'd be done, right?
Yeah.
Okay, so 1 minus x squared over 2. So since this, by cheating, is what cosine of x is equal to, then to know an expansion for x times the cosine of x without even having to do all of this stuff, all I gotta do is multiply every term by x. And so the actual f of x, let's see. No, the actual f of x is x cosine of x. That's the actual answer, but my polynomial approximation for it, I guess I'll have to figure out what I said on there, but I'll just say P6. And it's a function of x2 is, well, x times 1 is x times x squared is x cubed, x times x to the 4th is x to the 5th. And so everything just grows in x. And so, okay, great. That's not hard. But if I took the derivative of both of those, I'm supposed to get the same answer, right? So I'll wimp out and do the easy one first. So the derivative of and that's the whole point of this section, the derivative of a polynomial is really easy. And so the derivative of x is 1. The 3 comes down front. And then I have x squared over 2 factorial. The 5 comes down front. And then I have x to the 4th over 4 factorial. And the 7 comes down front, and I have x to the 6th over 6 factorial. So that's kind of what I've got for my answer. And so again, I'm thinking, man, if I switch to the derivative of f now, then I think, oh, okay, that's product rule. So the product rule says derivative of x, which is 1 times cosine left alone, plus x times the derivative of cosine, which is actually negative sine. And so I'm looking at these two going, huh? Wait, those aren't the same. Those don't even look close to the same. But cosine has an expansion. In other words, in order to get them to look the same, I got to write them all as polynomials. And so since we saw a minute ago that cosine was actually 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so forth. And then minus x times sine, well, that's minus x times whatever sine's expansion was, since sine's expansion was x. So minus all of this. Sine's expansion was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial and so on and so forth. But I got to multiply all of that by x still. So that means every one of these would grow another x. So x to the cube would become x to the 4th, x to the 5th would become x to the 6th, x to the 7th would become x to the 8th. So, okay, well, at least now this looks a little bit like, at least it looks kind of like this. Well, notice one good thing, look at all the exponents in my black one. All the exponents, there's no odd exponents. Well, that's good. So all I have to do is collect them together then. So let's take a look and see what we got. Well, I got a 1, but then look at your x squared terms. You got an x squared term here and an x squared term there. So that's really minus 1/2 x squared, since 2 factorial is 2, minus another x squared. Well, isn't that minus 3/2 x squared? Hey, that's what it was supposed to be. 2 factorial is 2. That is minus 3/2 x squared. Oh my gosh, it looks like it's actually working. What about my x to the 4th terms? Well, this is really x to the 4th. This is really 1/24 x to the 4th. And that's really minus, well, it's minus a minus, so it's actually plus 1/6 x to the 4th. If I get a common denominator by multiplying this top and bottom by 4, that'd be 1/24 plus 4/24, that'd be 5/24 x to the 4th. Oh my gosh, look at that. That's exactly what I got. 5 over 4 factorial, 5/20. They really are the same. How about that? Pretty cool. But ugly.
Hey, Doug, I wanted to ask you a question earlier in class. I think my algebra skills kind of failed me. Do you mind going back up to where you added, I think it was x squared plus 2 or something?
What problem was it?
I think it was, oh, this one right here.
This one?
Go up a little bit more. No,
Up
just
here.
up a little bit more, sorry. It's the red problem. Yeah, so you added x squared plus 3 to that. And I just didn't understand how you got 3 plus x squared over 2.
Yeah, so this one was intact. This one's like all good. And then I said, let's add 3 to it. Well, notice there's no constants in that yellow circle. So then if that's true, then I'll just have to add 3 to it. Right?
Oh, you're just adding 3?
Yeah, because it did say multiply. It's all added.
Oh, I thought you were adding x squared plus 3.
Well, I am. I added 3. Now I got to add x squared.
Okay.
So what do you add x squared to? Well, you don't add x squared to x. You don't add x squared to x cubed. You add x squared to x squared. So that's why
Oh.
it just got added to this term. So it's not multiplied. Multiplying, we'd have to multiply it by every term. It's added, so I can add it any place I want. Well, I've collected those together. So that'd be 1x squared minus 1/2 x squared. Oh, that's positive 1/2 x squared.
Oh, I forgot that was 1/2 x squared. Okay.
And then the rest of the terms, there was nothing to add to them, so they just got left alone.
Okay, thank you for clearing that up.
I'm glad you asked.
Have a good weekend.
You too, Cheyenne. Good luck on your test tomorrow. I don't think you'll need to.
Thank you. I'm sure I will.
Well, it never hurts. That's why I said.